Hey guys, it's Miss Miles. Today we're going to be talking about the scientific method. So I'm sure you're on day 3 of Unit 1, and that's how you got to this video in the first place. So we do have some notes that we're going to take over the scientific method. So eventually, you'll need to do that. So you'll need to get out your workbook. On your workbook, we are turning to page 1. So on page 1, we'll be taking some notes. So let's just talk about for a second what is the scientific method. So if you'll see here on the screen, it says let's learn the facts. So think about the scientific method is an approach that scientists and then people take in general just to solve problems. Just think about, maybe a time that you've solved a problem. And it doesn't have to be where you go, oh, I'm using the scientific method now, but it's just a method, a systematic way to approach problem solving. So say, for example, you drive and you're going to drive somewhere, maybe you're going to school, and you go outside and you go to start your car and it doesn't start. So what you might think is, you notice you left your lights on, they didn't shut off automatically, and maybe now your battery is dead. So you can start about, figuring out the problem, with your car. You might want to go and check your battery or change your battery. And then if you put a new battery in your car and it starts, then you know that it was probably the battery. Um, was the fault. Could there have been another problem there? Sure, there could have been another problem. But if you change the battery and your car then starts, then there's a good bet that maybe it was your battery was the problem. So the scientific method or scientific thinking is just a way to systematically try to solve a problem. So if you look at your screen there, we are looking at just scientific thinking. It says science as a way of thinking, questioning, and gathering evidence. I really like this picture here. This is a mosquito. So this is taken with an electron microscope. We'll get to microscope soon. But an electron microscope will take very detailed pictures of objects that are really, really small. So you can see, his antenna, you can see his mouth parts, and more importantly, you can see all of the lenses of his compound eye. So that's a pretty cool picture right there. So on this next one, we're just looking at the steps of the scientific method. And so, on your notes in just a second, your notes are really just a linear procedure. Whereas if you look at your screen, it's really a circular sort of procedure. But that's okay. Lots of times, scientific method is written out in a linear path. For example, maybe on a poster or something that where it's posted, you might be able to see that. But scientific method is really just a way of life for scientists, and it's something that is always happening. It's always going on. So thus the circular pattern here that you see on the screen. It says scientists make careful and systematic observations. So scientists have to be careful with their observations. We talked about the metric system on day 2. And so with the metric system, you have to take careful, accurate, and precise measurements. And then once you collect your data, you're going to put it in some sort of table or chart. But before you can get to an experiment, you have to start with your hypothesis. Think of hypothesis. Sometimes people want to say educated guess, but when you use the term like educated guess, that sort of guess just, invites in thoughts like you're just guessing, like you just have no clue, but you're just gonna, have a shot in the dark here. But really, a hypothesis is you've done research and you know maybe what's causing it. For example, on your car not starting, you have prior knowledge that cars need batteries. They need the juice from a battery to be able to run. So you have prior knowledge. It may be not something that you have to necessarily investigate or research, but if it's a scientific problem, you may have to do some research to develop your hypothesis. And then once you have your hypothesis, you're going to run an experiment, you're going to collect your data, and then you're going to have to analyze that data and come up with any conclusions. So if you look here at your screen, observing, you're making some sort of observation. It can be an observation in nature. Maybe you're asking a question, why does this happen? or what does this mean? And then you're going to form a hypothesis. Remember, a possible answer. You're going to test it with an experiment. You're going to collect your data, analyze your data, and then you're going to draw your conclusions. You're going to evaluate those results. And it's really in a circular pattern here because many times you just have to start right back over. We have to be able to, as scientists, make sure that we can duplicate our own results, share those results with the scientific community. That's why there are all those scientific publications that get published with all of this scientific research. You have to have peer review. That's a big part of the process. You have to have other scientists come along and say, okay, let's look at your research. Let's look at your experiment. Let's see, what you've done. And they have to come along and say, is it good or is it not so good? Um, the next thing, variables and controls. When you set up your experiment, you have to have certain variables and you have to have controls or at least constants in place. Um, I always like to think of an independent variable as starting with the word or the letter I. So, an independent variable is the thing that I am changing, the thing that I am testing in an experiment. Dependent variable starts with a D. So I always think of D standing for data. A dependent variable is the data that we're collecting. And then constants are those conditions that we try to keep the same. So we'll get to a couple of scenarios here in just a second, and so we'll be able to, pinpoint all of those things in a scientific experiment. So the next thing, I really like this chart. This is what I was talking about earlier. Independent variable starts with an I. It's what I change. It's what I am testing. Dependent variable starts with a D. It's what I observe. So I always think of the data that you get when you're doing an experiment. And then a controlled variable or a constant, things that you're trying to keep the same. If you are trying to see if a new battery will help your car to start, and then at the same time you change the battery, you also change the spark plugs in your car, then the car starts. You don't know if it was the battery or if it was the spark plugs. So you have to try to make sure that you keep everything the same except your independent variable, the thing that you are testing. And so we'll talk about a couple of scenarios in just a second. I really like this diagram here. This is showing three plants. You have three plants, plant A, plant B, and then plant C. You're trying to determine in this experiment in what liquid will plants grow best. Obviously, we have a lot of background knowledge already on that, so we know that plants will grow best in water, or if given water. But in this case, we are looking at plant A. Plant A, they're adding soda to this plant to see if it will grow. Plant B is getting juice. They're adding juice to this plant to see if how it will grow. And then plant C, they're going to add water. So what they're doing every day, they're adding the same amount of each liquid every day. They're taking the growth. They're using a ruler. They're measuring the plant height daily and then recording that in a data table. Um, but the thing that you have to remember here, now we know that plant C is probably going to have the best growth, but we are testing. How does juice affect plant growth? How does soda or Coke affect plant growth? But what we have to do here is have just one independent variable. So we just have to have one independent variable. So our independent variable in this scenario is the type of liquid. We can't change too much here. We have to just make sure everything else is the same. So we have the same type of pot that the plants are planted in. We have the same type and same species of plant. We have the same soil, same amount of fertilizer every day, and then we make sure that they all get the same amount of sunlight. We're going to put all of these pots or these plants in the same window, and they're going to get the same amount of sun each day. So we are narrowing down to make sure that everything is left the same except our one independent variable that we're testing. If everything else is kept the same, That is our constants. Those are the things that we keep the same. We also have this control group here is plant C. Our dependent variable will be the data that we collect. Every day we're going to measure each one of these plants and we're going to put it in a data table. That's our dependent variable. That is the plant growth or the plant height, and that depends on our independent variable. That depends on the liquid that we're giving them. However, let's say we took plant B and we put it in the back room with no sunlight. We can't do that in an experiment because that would be changing two different things, and we need to make sure we only change one thing. So we need to make sure that everything is kept the same, everything is kept constant, except for our independent variable, that one thing that we're changing. And in this case, it's the liquid, and we're trying to test in which liquid plants will grow best. So that's just a little scenario. So hopefully that will help you to understand that a little bit more. This is a scenario here. I'm not sure if you can see it very well, but we'll come to other scenarios on your work today. So we'll skip that for now. I do want to talk for a second about the word theory. It says theories explain a wide range of observations and experimental results. Theories can change based on new evidence. Now, you probably know lots of theories. You probably know the theory of evolution. You probably have heard of the Big Bang Theory. There are lots of theories that we use to explain the world. A theory, sometimes theories get a bad rap. Some people think, oh, that's just a theory. There are theories, there are laws. A law like the law of gravity, we know that gravity is going to pull everything down to the center of the earth. That is a law that we live our life by. We know that if we get it up into an airplane, or if we throw an object into the air, that those things can possibly fall down to earth. So laws are different than theories. A theory is something that has scientific evidence backing it up and is generally accepted by the entire world. But for example, like the Big Bang Theory, there's lots of evidence. The theory of evolution, there's lots of evidence for evolution in our fossil record. But you know, those are things we weren't here at the beginning of the universe. So those are theories that have been put forth to explain those things. But then there are lots of evidence backing up those theories. I do want to talk a little bit about this picture here. This picture is showing bacteria growing in a stomach lining. So I don't know if you've ever heard of someone having stomach ulcers. A stomach ulcer is a spot in your stomach that will grow. It'll be like a raw, irritated place in your stomach. And forever, even when I was growing up, people would talk about stomach ulcers as being a result of a lot of stress in your life. So if you had a high stress job and you were under a lot of stress, quite frequently you could develop stomach ulcers. Well, a scientist came along and he said, wait a second, I'm going to debate that theory and I'm going to propose a new hypothesis. I think that stomach ulcers aren't necessarily just caused by stress. I think they're caused by bacteria, and I think they're caused by specific bacteria. So that's what this picture right here is showing. It's showing a stomach lining with this bacteria. In fact, the scientist was so adamant about it, he actually ingested on purpose the bacteria. And guess what? He developed stomach ulcers. Stomach ulcers now are typically treated with an antibiotic. I do believe that there is a component of stress with stomach ulcers, though, that some people, given the bacteria and maybe stress in their life, they will develop stomach ulcers. But that's a breakthrough because now people with stomach ulcers, they can have a prescription for an antibiotic and then they can be cured of their stomach ulcers. So that was a new theory, a new hypothesis that was put out, and then the scientist was able to back that up. I mean, he used himself as a guinea pig, which is probably not the best thing to do. But there's been several different experiments after that that have backed up his research there. So that's just an interesting little side story there, just letting you know about stomach ulcers. Really quickly, we're going to go from this screen and I'm going to take you to your home page. Oh, sorry. I guess I need to save something before I go. Okay, so if you will go to your home page, I think it's good. Okay, so if you'll go to your home page looks like this. And if you will click on your assignment for today, it's called 1.04 scientific method. And you can go ahead and bring that up and we'll get to that in just a second. Also, in your workbook, if you will turn to page 1 of your workbook, we are going to take some notes. So on page 1 of your workbook, this is what this looks like. And we're going to take some notes about our scientific method. So if you'll notice on this page here, it says scientific methodology. Number 1 is observing and asking questions. You always have to ask questions in the world to try to get an answer for those. And, scientists will often observe nature and then they'll ask questions. Why does this happen? What causes this? There's all different sorts of questions that can be asked. You have to make sure in science, though, that it's a good question, that it's a question that can have some maybe proof to back it up. For example, if you ask the question, what happens to us when we die? I don't know a lot of people that have died. So that may not be a question that can be answered. So you have to make sure that you're posing good questions, and not every question can be answerable, so to speak, but we can get proof that possibly that is the correct answer. So on the first step of the scientific method, observing and asking questions is already written in. After you have asked a question, and you might have that worded as defining a problem. Observing and asking questions is the same as defining a problem. So, for example, you go out, your car's not starting in the morning. That is a problem, and you need to fix that problem. The next thing we're going to do is develop a hypothesis. Remember, we need to step away from that definition of educated guess, and we need to think of a hypothesis as being a possible answer. So you have asked a question or you have identified your problem. You're going to develop a hypothesis. I do want to add a little word between these two steps because you probably have to do some research. The scientist that was working to solve the mystery of stomach ulcers, he had to do some research. Okay, let's look at this. Let's look and see exactly what is causing ulcers to develop in people's stomachs. And he had to look at a lot of previous studies and research before he developed his hypothesis. So you're going to ask questions. You're going to do a little research. Then you're going to develop a hypothesis. The next thing you're going to do, you're going to conduct an experiment. Now, remember, when you're conducting an experiment, you have to make sure that you do it correctly and you have an independent variable, a dependent variable, and then you might have a control group. If you don't have a control group, you may just have constants, things that you try to keep the same. Your independent variable, I really like to think about and highlight and circle this I here, and I'll just highlight it for you. I think about the things that I change. Think about the things that I am testing. If you can think about that and remember that, then that will help you to determine your independent variable. Dependent variable, if you can think about the word data or data that starts with D, the dependent variable is the data that you're going to collect in an experiment. So once you've set up your experiment, you have only one independent variable, and then you collect your data with everything else in the experiment remaining constant. You're going to collect that data. You're probably going to put it in some sort of graph. We will get to graphing soon, but I'm just going to do a little graph right here for you. I'm just going to draw a graph. Now, the thing with a graph, Your independent variable, and I'm just going to do IV for independent variable. Your independent variable usually goes on your x-axis, and your dependent variable usually goes on your y-axis. So that's typically how you would set up a graph, but we will get to some graphing in the future. Once you have your data, you've collected your data, you've put it in a table, you've put it in a graph, you need to draw your conclusions. You need to determine, am I correct? Did my hypothesis, was it supported by my data? Did I have enough evidence to say, yes, I can say that my hypothesis was supported by my data? Now, you may not ever be able to prove beyond a shadow of a doubt that your hypothesis is correct, but failures in science are just as good as successes, because you can say that a hypothesis is falsifiable, that it's false. You definitely can say that. But we can't sometimes account for the weird things in life that happen. There is sometimes these unexplainable phenomenon. Usually everything is backed up, in science. But we don't want to actually say that we were right, that it was proven. We typically want to say that our hypothesis had evidence to back it up. And so once you're finished with that, you have to make sure that you can repeat, your whole experiment, that you can repeat and get the same results. And then it's really important also to share your results. Um, all of these scientists will publish in some sort of scientific magazine, or they'll just publish their work. And then they'll have other scientists read it, and it'll be peer reviewed. And so those are the scientific breakthroughs that we need to be paying attention to, because if it's repeatable and other scientists have said, yes, this is good solid science, then those are the ones that we have to make sure we pay attention to. And I also want you to draw a line right back up here to the top. Remember that circular pattern that we had on our previous example? You have to be able to start all over again as well. You have to be able to repeat, your experiment and get those same results. So that's more of that circular pattern that we were talking about earlier. So that's it for your notes on page 1. You do have, and I'll skip this really quickly right here. You do have this, I believe, this graph here on page 3. I do want you to try to go ahead and turn to it. I believe it's page 3. I don't have the workbook right in front of me right now. But I would like you to take a look at this. So turn in your workbook until you see this diagram here. This is showing a graph. And then on the graph, you see the title at the top, plant height. You have to make sure whenever you're reading graphs that you really look at your titles, because your title can show you lots of good information. And then also look at your x-axis and your y-axis. We can see here that we have some more information below our x-axis there. Our x-axis is labeled as time in weeks, and then our y-axis is labeled as height here. Below that, we have two different lines. We have one nitrogen, and then the other, which is our control. I'll just do those in two different colors, so that'll make it a little bit brighter for you. So this is our nitrogen line right here. And then this is our control group. Remember, our control group will not have our independent variable. And so that's our control group. So we can see just by looking at this, if we're talking about two different plants, let's say we have plant A up here and we have plant B right here. When we're talking about two different plants, we can see that plant A, the one that had nitrogen added, had more growth than our plant B, the one with the control. So what it's wanting you to do here is identify your independent variable. So remember, think about independent variable. We want to think about that I at the beginning. You want to think about the thing that I am changing or the thing that I am testing. So the thing that they're testing here is nitrogen. So remember, in one of these groups, one of these plants, they added nitrogen to the plant. And remember, nitrogen is a big component of fertilizer. Fertilizer really is nitrogen, and plants need nitrogen in order to grow. Nitrogen makes up about 78% of our atmosphere. Nitrogen is not in a usable form in our atmosphere. So we have these little bacteria that grow at the roots of some plants, and they fix nitrogen into a usable form for plants. And we'll talk about that more when we talk about the nitrogen and the phosphorus and the carbon cycle. Number 2 says identify the dependent variable. So I want you to think about dependent variable starts with a D. And so you can remember the word data. And so this is the data. These are the measurements that you take when you are doing a lab, when you're doing an experiment. So here our dependent variable is the height. How high or how tall did these plants grow? And that's our dependent variable. That is the data that we measured. Every day we would come along for weeks in this case, and we would measure these plants and then we put it in a graph to show that the nitrogen added plant did grow taller than the one with no nitrogen. Number 3 says which plants grow taller, those in the experimental group or those in the control group. So what I'll need to show you right here, I'm just going to label these. This one where the nitrogen was added is our experimental group. Our experimental group will have our independent variable. Our control group will not have our independent variable. So think about which one actually grew taller. It's going to be the one in the experimental group. So our E group was the one, and you can write out the word experimental there. Our E group, our experimental group, was the one that grew taller. And then number 4 says, describe why this is a controlled experiment. Well, first of all, it's a controlled experiment because we have a control group. Now, sometimes you'll do an experiment and you won't have necessarily a control group, but it is still a controlled experiment as long as you have just one independent variable. So in this case, we do have a control group. We have a group that is our experimental group that got nitrogen, and we have a group that's our control group with no nitrogen. But remember, when you're doing an experiment, you have to have one independent variable. So if you have more than one variable, you're not going to know if your results came from the thing that you were testing or if it came from something else. So just make sure anytime you're looking at an experiment, they should have just one independent variable. And that's taken me a while to write that. But if you look at these two plants, what if we had taken one of those plants and we had put it in a dark room with no sunlight? We wouldn't know if the lack of growth was because there was no sunlight and the plant ends up dying, or if it was because of the change in or the difference in the nitrogen between the two groups. So a controlled experiment usually has a control group, but if there's not a control group necessarily, we need to make sure we only have one independent variable. Okay, so moving on. I'm going to skip these things. We'll come back to those. You have your assignment today is labeled scientific method. So I'm going to go through a few of these things with you here and just get you started on it. You also do have a Pearson Realize, but remember video 1A, that introduction video walked you through Pearson. So if you don't know exactly what to do on that, go back to video 1A. You can fast forward to the point where I get to the Pearson, but you do have a Pearson assignment today on scientific method. So if we'll look at this is looking at a picture here, and I'll go and show you this picture just a little bit larger. So this is a Compatosaurus and a Stegosaurus. So this guy, we can tell he's a meat eater. This guy is definitely a plant eater. So these two dinosaurs are here in this picture, and we're looking at observations versus an inference. Where you're gonna determine, are you observing it, are you seeing it, or are you sensing it with your five senses, or are you making an inference from this picture? So, a good way to remember this, an observation. Let's say you look outside and it's raining. You can see raindrops falling from the sky. That would be an observation. Let's say you're in the middle of the school, there are no windows, but you see everyone entering the school and they have umbrellas, they have on raincoats, they're dripping water. You can infer, even though you can't see outside or hear the rain at that point, you can infer, yes, it is probably raining outside. So, an observation, something you observe with your five senses, an inference, something you infer from prior knowledge. So, number one, the volcano is erupting. This one, it can be debated a little bit, but I can look right here in this picture. And if I go to the bigger picture and circle that here, I can see with my senses that there is truly smoke coming from the volcano. So that is definitely an observation. Number two, the Compatosaurus is going to eat the Stegosaurus. Now, this guy, Compatosaurus, may end up eating the Stegosaurus since he's a carnivore and he's an herbivore. Um, but is that happening in the picture? If that's not happening in the picture, then that's an inference. We can infer that that may happen, that the Compatosaurus may have the Stegosaurus on his diet, but right now that is not happening. Number three, the Stegosaurus will run into the water to escape. Well, the Stegosaurus is not currently in the water. He's just over here munching on some of his plants. But if the Compatosaurus did get after him, then I could see that the Stegosaurus, might run into the water. But that would also be an example of an inference. Number four, we'll stop at number four. You will continue on and do the rest of these on your own, but this will just give you a leadway into knowing how to do this assignment. Number four, the Compatosaurus is leaving tracks in the ground. Well, let's go look at the bigger picture here. We can see that these footprints pretty much match that Compatosaurus. So we can say that that is an observation, right? We can see that. So go through and determine if you can see it in the picture, it's an observation. If it's something that you have to infer from prior knowledge, then it's an inference. Okie doke. So let's move ahead. On the next part, you have qualitative versus quantitative. You do have a definition listed there for you on your assignment. But real quick, I'll just go through qualitative versus quantitative. When you're talking about qualitative, we are looking at the quality of something. So, for example, the book is red, the boy is tall. Something that does not have a number with it. The car is loud. So, all of those things I have observed, but they are qualitative measurements. They are talking about the quality of something. Quantitative will have a quantity with it, it will have a number associated with it, usually a number in units. So, quantitative, we're looking at a quantity. So, let's do a couple of these together. Number 11, the cup had a mass of 454 grams. Now, we can see a quantity. Qualitative might be where you say the cup is heavy or the cup is light, but this one has a specific number and a unit with it. This is a quantitative observation. Number 12, the temperature outside is 25 degrees Celsius. So I haven't just said, oh, it's hot or it's cold outside. I've given a specific measurement here. So again, that's a quantitative observation. I am giving a number with a unit. Now, on to 13. It is warm outside. Warm outside, I don't have a number and a unit to go with it. So that is a qualitative measure. And I'm just talking about the quality of it. I'm talking about the aspect of outside with not a specific number and unit to go with it. Number 14, I'm saying the tree is 30 feet tall. So if I have a number here, It's not wanting to write. If I have a number here, 30 feet tall, I can see that that is definitely quantitative. I didn't just say the tree is tall. I didn't say the tree is short. I gave a number with it. So that should help you get started on that, qualitative versus quantitative. The next couple of parts of your assignment, you have some scenarios. On these scenarios, we will have to go through and determine independent variable, dependent variable, and then controls and constants. The first one that we're going to go through talks about scurvy. These are characteristics of scurvy. I don't know if you've ever heard of scurvy. It is a disease. We now know that the disease is caused by lack of vitamin C. People that were passengers or sailors on ships, they would sometimes develop scurvy because they would run out of fresh fruits and vegetables to eat, and they would develop scurvy. Scurvy, the first stages, you could be really tired. Eventually, you might show bleeding from the gums. You would show anemia, which would again make you very tired. You might get spots on your back. You might develop a high fever. If it was severe enough, you may die. So scurvy was something that affected a lot of people that were passengers or sailors on ships. So we'll come back to this one, Francisco Reidy's experiment, in just a second. So this is the first scenario on your page. If you look at it, it says in 1747, while serving as a surgeon on the Salisbury, James Lind carried out a controlled experiment. So it goes on to tell you exactly what he was looking at. He was looking at 12 men from a ship, and all of these men were suffering from scurvy. He divided the men into 6 pairs. So he had 6 groups of 2. What he started doing with these men is he was giving additions to their basic diet. So all of these men were living with other men on this ship. They were sailing at the time. And then he took these 12 men that had scurvy, he divided them into 6 groups, and he was giving them things in addition to their regular daily diet. So, one thing that he was giving 2 of them was a quart of cider every day. Not too bad. The next group, they got 25 drops of sulfuric acid 3 times a day on an empty stomach. That probably would not be very good. The next group, they got 1/2 pint seawater. Seawater apparently was in abundance, right? They're in the ocean. So they were able to take 1/2 pint seawater every day. The next group, they got a garlic, mustard, and horseradish in the lump, the size of a walnut, and they had to take that every day. That kind of sounds disgusting. The next group, they got 2 spoonfuls of vinegar 3 times a day. And the last group, they're probably in the best group. They got to eat 2 oranges and 1 lemon every day. Remember, on these ships, when they were out to sea for weeks at a time, they would run out of fresh fruits and vegetables. So sometimes fresh fruits and vegetables were hard to come by. It goes on to say the men who had been given the citrus fruits recovered dramatically within a week. One of them returned to duty after 6 days, and the other became nurse to the rest. The others experienced some improvement, but nothing was comparable to the citrus fruits. Well, we now know that scurvy is actually caused by a lack of vitamin C. We also know that citrus fruits are very high in vitamin C, so that proved to be a cure for their scurvy. So on your page, you have all of these things that you need to answer. So the first thing is independent variable. So you need to ask yourself, what was being tested? What did he change for the 12 men on this ship? So the thing that he tested, he gave them additions to their diet. So they had a regular diet that everybody else on board had, and he gave them extra additions to the diet. And he was trying to test to see which additions would actually cure scurvy. Dependent variable, the thing that was measured, our data. In this case, it's if they were cured of scurvy or not. So those people were watched, and then if they were cured of scurvy, then they knew that, hey, that was a possible cure for scurvy. We have two groups here, our control group and our experimental group. Your experimental group is probably easiest to figure out. It's the ones that are being experimented on. Oops, sorry, I've got the wrong one. So that would be the 12 men. So the 12 men were in your experimental group. They had your independent variable. So I'm going to draw a line right back up here to this. Our independent variable is in your experimental group. So remember, in your experimental group, it will contain your independent variable. So I'm going to write IV right next to that. So we'll know that our experimental group contains our independent variable. Our control group has no independent variable. Your control group does not contain your independent variable. So which group was our independent variable, or which group was our control group? Sorry. Our control group was everyone else on the ship. So these 12 men, hopefully, when they were cured of scurvy, then they were compared to everyone else on the ship. We want to make sure that, they're all living in the same sort of conditions, and the only thing that's being changed are the additions to their diet. So there were constants that, were on the ship. Really, these men there were on the same ship. They had the same regular diet. They were breathing the same fresh air, same living conditions. So they were constants just because they were on the same ship. Your hypothesis can be written out several different ways. Your hypothesis can be written out as a question. It can be written out as an if-then statement, but typically your hypothesis will contain both your independent and your dependent variables. So I've written this one out. If men are given additions to their diet, then they will be cured of scurvy. So that contains both our independent variable, our additions to the diet, and it also contains our dependent variable, whether or not they're cured of scurvy. Now, you could write that in a question form. You could say, which diet additions will cure scurvy? There are several different ways that you can identify that. Now, if you don't do a hypothesis, make sure you at least write down a question or the problem that we're trying to solve. In these cases, pretty much our hypothesis, problem, and question are pretty much all the same. So you have two more scenarios to work through on your page. I did want to show you really quickly this one. The second scenario talks about Francisco Reidy's experiment. And it talks about this experiment because of this previous thing known as spontaneous generation. A long time ago, people believed that living things could come from non-living things, which is kind of crazy. You should know that frogs like to get down in the mud. They hibernate. And then when people would see frogs come out of hibernation, out of the mud, they would say, "Oh, look, that mud just made those frogs," which is crazy in and of itself. Also, people would say when they saw meat that had set out and it was exposed to flies, eventually maggots would develop on the meat. And they would say, "Oh, look, that meat just developed those maggots. It produced those maggots," which is sort of a crazy concept to us now. But that was a concept at one point. So that had to be proven wrong. So that was proven wrong by this experiment, Francisco Reidy's experiment. What he did, he took 3 bell jars. So we have 1, 2, 3 bell jars. Your experiment just explains it a little bit different. There might be 4 on yours. But what he ended up doing here is that he left one of these exposed. All 3 of these jars had the same type of meat, same size of raw meat placed in them. And what he was noticing, when it was left with no covering, flies were able to get in there to the meat. They laid their eggs, which was turned into the larvae, which were maggots. And we know that maggots are just the babies of flies, the larvae of flies. And so, of course, they are attracted to this decayed, rotting meat. When flies lay their eggs there, they lay it on the meat. So, the larvae or the maggots will have a food source. So instead of saying, "Oh, look, that meat produced these maggots," we know that maggots are, just developing from the eggs of flies. But this had to be proven, and Francisco Reedy was the one that did that. He took another jar and he would place, on this one, he placed a cork stopper. Flies couldn't get anywhere near it. Again, no maggots. Over here, he took a piece of cheesecloth, and I think your experiment talks about the cheesecloth, where the flies could still smell the aroma. So they could still smell the smell of the rotting meat, but they couldn't reach the rotting meat. So they just laid their eggs on the top of that covering, the covering of the jar there, in hopes, I guess, in hopes that the maggots could eventually get to the meat. So this proved that, maggots were not developing from the rotting meat, but they were actually the larvae of flies. And even though, the flies couldn't get to the meat here, they could still smell the meat. So, they laid their eggs near that rotting meat source. Here, no eggs were laid because they couldn't even smell the meat in that case. So that should hopefully get you started on your assignment. So remember, today's assignment is 1.04, scientific method. And then you also have a Pearson Realize. I will show you on your Pearson Realize, and just remind you again, that link will take you to your class link. Once you get on class link, you'll click on Pearson Realize, and that will take you to your assignment. You may have to log in like I'm having to do right now. But once you log in, just go in and you will be completing your interactivity on scientific method, and you'll also be doing a quiz over scientific method. Please watch the Amoeba Sisters video on scientific method, because that will help you to understand scientific method a little bit better. But remember, we completed those 2 worksheets today in our workbook. Your workbook will be graded as a grade, and it's a place for you to take notes and for us to interact with our notes. But once you're finished with today's assignment, go to Pearson Realize, click on Lesson 1, What is Science? And you have 2 activities to do. I walked you through these activities on the very first video, video 1A. So if you need a reminder for that, you're welcome to go and look at that video as well. But there is, sorry, this is taking forever to load. There is the interactivity there. And remember, this is talking about the advent or the creation of vaccines. So remember, on this particular one, he's using the scientific method. You have to read what he's doing, click on the scenario, click on the scenario, click on the scenario, and it'll walk you through. And the cool thing with that was that, the women that were the milkmaids, they would develop cowpox, and the cowpox, they would not die from that. And so he theorized, Dr. Jenner theorized that that women who developed cowpox then were immune to smallpox. And so he took some of the pus from the pustules that would develop on the hands of the milkmaids, and he actually made one of the first vaccines. And so that was, just showing the results of his experiment using the scientific method. So once you're finished with that, you click on that and you don't have to start over. But down in the bottom right corner, you'll be able to go to the next page and complete that. Once you're done with interactivity, make sure you go to your quiz, and then you can walk through your quiz. Try to do your best job. This is a pretty difficult quiz, but try to do your best job on that quiz. And then if your score is really low, you'll get a remediation that will just give you more practice. Okay, so that's it for me today, and let's go do some biology. Bye.